In today's class for solid state pharmaceutics, we will talk about intermolecular interactions in crystals. Let us first look at the terminology supramolecular chemistry. Supramolecular chemistry is a terminology related to crystal engineering. It is defined as the chemistry beyond the molecules, the science of non-covalent interactions between different molecules, or the science of or the science of non-covalent intermolecular interactions. Just as there is a field of molecular chemistry based on covalent bonds, there is a field of supramolecular chemistry, the chemistry of molecular assemblies and of intermolecular bonds. The significance of supramolecular chemistry lies in the fact that the assembly or collection of molecules has a structure and properties that are more than the sum of its parts. In other words, supramolecular aggregates will have or will confer different properties to the material which are not attributable to the individual molecules, but they are rather because of the group of molecules. The differentiation between intramolecular and intermolecular interaction lies in the strength of interactions. Intramolecular interactions that hold atoms together in a molecule are covalent bonds and have bond energies in the range of 75 to 125 kilocalories per mole. In contrast to that, intermolecular interactions that hold molecules together in a crystal have energies in the range of 1 to 20 kilocalories per mole. It is quite apparent that the strength of the intermolecular interactions which are at play in the crystal lattice is much less as compared to the intramolecular interactions which are responsible for formation of a single molecule. Both bonds and intermolecular interactions are electrostatic forces of attraction or the Coulombic forces. However, they differ in the locations of the areas of charge and the magnitudes of the areas of charge. As a result of these differences, there are significant differences in the strengths of the resulting interactions. We are now going to concentrate on the intermolecular interactions that are responsible for formation of the crystal lattice. We are not here discussing the intramolecular interactions which are responsible for formation of a molecule. Those interactions are primarily covalent interactions, while the intermolecular interactions are non-covalent in nature. The intermolecular interactions can be described based on three attributes. The first attribute is strength, second is directionality, and the third one is distance dependence. The intermolecular interactions could be weak or strong. Now we are not talking of the covalent interaction. These are all non-covalent interaction. Within that, there could be certain weak interaction and strong interactions. There is no clear-cut demarcation between what is weak and what is strong interaction. And intermolecular interactions are in the range of 1 to 20 kilocalories per mole and sometimes 0.5 to 5 kilocalories per mole. We will be discussing the broad ranges that are involved in different intermolecular interactions, which makes them either strong or weak. The second attribute is that of directionality. Some of the intermolecular interactions are isotropic in nature, which means they lack directionality. In other words, they are similar in all the directions, while there are other interactions which are anisotropic, which means they exist only in one direction. The third attribute is that of distance dependence. Electrostatic have inverse distance dependence, while the dispersive forces like van der Waal interactions have inverse sixth power dependence. We will try to understand what we mean by this, that the electrostatic interactions, which is part of the intermolecular interaction, have a inverse relationship with the distance, which means if the distance increases, the strength of the interaction decreases, while the dispersive interactions like van der Waal interactions have a inverse sixth power dependence, which means even if the distance increases slightly, they will become very weak, which means the relationship between the distance and the strength of the interaction is much more prominent in the case of dispersive interactions, which are also van der Waal interactions, and they have a inverse sixth power dependence. There are three different types of intermolecular interactions which are responsible for keeping molecules together in the crystal lattice, especially in the molecular crystals. We are in this class mainly going to talk about organic molecular crystals because most of the drugs are organic molecules, and that is what our interest would be. As against that, there is also a field of inorganic crystals where we discuss crystals of sodium chloride, potassium chloride, barium chloride, etc. However, in the case of drugs, the structure is an organic molecule, and that is what we are going to discuss more in this particular class. There are three types of intermolecular forces: hydrogen bonding, dipole-dipole forces, and London dispersion forces. Hydrogen bonding are the strongest non-covalent interactions that are available in the crystal lattice. They are dependent on availability of polar structure. They are anisotropic in nature, which means they have directionality, and the strength of their interaction is 1 to 12 kilocalories per mole. Dipole-dipole interactions lies between hydrogen bonding and London dispersion forces, which means the strength of these interactions is in between hydrogen bonding and London dispersion forces. They are also an outcome of the polar structure. They are also anisotropic in nature, and the strength of the interaction is 0.5 to 2 kilocalories per mole. London dispersion forces are weakest in nature and they occur in the non-polar part of the structure. They are isotropic, which means they lack directionality or they are equal in all the direction, and the strength is less than 1 kilocalories per mole. Hence, you can see in the case of hydrogen bonding, the strength is 1 to 12 kilocalories per mole, while in the case of London dispersion forces, it is less than 1 kilocalorie per mole. In comparison to this, covalent bonds have energies in the range of 75 to 120 and up to 400 kilocalories per mole. This means that covalent interactions are strongest, while the intermolecular interactions that are responsible for keeping the molecules together in the crystal lattice structure are much weaker as compared to the covalent interactions. Within the category of intermolecular interactions, hydrogen bondings are the strongest types of interaction, while London dispersion forces are the weakest interaction, and in between them lies the dipole-dipole interactions. The general representation of the hydrogen bond is given in this slide. This is the anatomy of a hydrogen bond. This is the hydrogen bond acceptor or a Lewis base, while this is a hydrogen bond donor or a Lewis acid. there is a partial negative charge on the molecule, on the group here, which comes from the hydrogen bond acceptor, while there is a partial positive charge from the in the structure of the hydrogen bond donor. There is an electrostatic interaction between these two because of the opposite charges that exist. This A could be electronegative atom like nitrogen, oxygen, or sulfur. Here the D is nitrogen, oxygen, or sulfur. Between them is a polar or a covalent bond. The IUPAC recommended definition of hydrogen bond is that it is an attractive interaction between XH and YZ, between a hydrogen atom from a molecule or a molecular fragment XH, in which X is more electronegative than H. This is the part we are referring to. So this is more electronegative than the hydrogen atom, and an atom or group, and an atom or a group of atoms in the same or a different molecule in which there is an evidence of bond formation. Bond formation is indicated by the shorter bond length that is observed. So this is the hydrogen bond donor. So this will donate this hydrogen atom, while this is the hydrogen bond acceptor. Because of the presence of the negative charge here, it will accept. And the bond that is going to be formed between them will have a shorter length, and that is indicative of the formation of the hydrogen bond. The list of criteria for hydrogen bond formation between XH and YZ is: the forces involved in the formation of a hydrogen bond include those of an electrostatic origin. The HY bond strength increases with increase in the electronegativity of X. This bond increases as the electronegativity of X increases. Sorry, the HY bond strength increases with increase in electronegativity of this particular group. So this will become shorter. If this becomes shorter, it means the bond has become stronger. The XHY angle is closer to 180 degrees. So this bond has an angle of 180 degrees. However, the deviation from 180 degrees to 110 degrees is commonly observed in pharmaceutical molecules. Shorter is the HY distance, the stronger is the hydrogen bond, and the HY distance ranges from 1.5 to 3.0 angstrom. So this distance between XH and YZ is 1.5 to 3 angstroms. Shorter this distance, more stronger is the bond. The length of the XH bond usually increases on hydrogen bond formation, leading to a red shift in the infrared XH stretching frequency. When this bond is formed between H and Y, the distance of this bond will increase because this hydrogen has now started participating in bonding with Y. So this will be reflected in FTIR as a red shift. The XH-YZ hydrogen bond leads to characteristic NMR signatures that typically include pronounced proton deshielding for H in XH. So this proton deshielding will take place, and this will be reflected in the NMR spectra. The difference between dipole-dipole forces and hydrogen bonding is very subtle or very small. When a hydrogen is directly bonded to a nitrogen, oxygen, or fluorine, then the system will be capable of hydrogen bonding, or else the system will get into dipole-dipole bondings. Coming to the van der Waals interactions, for the purpose of molecular chemistry, For the purpose of molecular crystals, van der Waals interactions are a sum of all stabilizing and destabilizing interactions, but excluding the hydrogen bond and other anisotropic interactions such as dipole-dipole interactions. It includes induced dipole interactions or London forces. They are very weak in nature, but they are very high in number. That is why they are numerous. They can affect the solubility, density, and melting point of the compound, and they are considered to be one of the most important contributors to the crystal properties. This pictorial depicts the van der Waals interactions, and they occur between the non-polar systems. Look at this part of the molecule. Electrons are temporarily shifted to the end and create a temporary dipole. So this is a temporary dipole that is created because electrons have shifted here, and electrons are driven to the end of the neighboring molecule because of the temporary dipole established next to it. So because of the formation of this dipole here, the electrons will be shifted to the other end of the neighboring molecule, leading to the formation of an interaction or an attractive interaction between these two parts of the molecule. This is called as the temporary dipole, and this is called as the induced dipole. And the interaction that happen between these two parts of the molecule are called as the London dispersion forces. Remember, they are very weak, but they are very large in number, and they are isotropic, which means they are not differing in different directions, and they have a very important role to play in the properties of the crystals. There is a very interesting aspect that comes because of the van der Waals interaction, and it is called as the Gulliver effect. As compared to hydrogen bonding, van der Waals interactions are much weaker in nature. However, a large number of these weaker interactions have considerable effect on overall crystal packing as compared to few strong interactions like hydrogen bonding and dipole-dipole interactions. This phenomena is referred to as the Gulliver effect in the area of engineering of molecular crystals. What it shows here is a bigger molecule or a set of molecules, and they are held together by these small threads which are very large in number, and these are called as the van der Waals interactions. So these small threads are indicative of the van der Waals interactions. In fact, this is a story which is taught in the early years in our school days. The title of the story is the something related to Gulliver, the tales of Gulliver or something. So here the threads are representing the or the van der Waals interactions are being represented by threads, since they are so large in number that they are able to held together even the bigger molecules in the crystal lattice, and they are going to be an important contributor to the properties of the molecule. Another important aspect related to the crystal packing is called as the Kitay-Gorski model of close packing. It is the name of a Russian scientist who had proposed this model of close packing. It says that the molecules in a crystal tend to assume equilibrium position so that the potential energy of the system is minimized. Attractive and repulsive forces between molecules are assumed to be isotropic, which means they are equal in all the directions. Molecules tend to approach each other so that the number of lowest energy interactions is as large as possible. The number of intermolecular contacts in a crystal tends to be a maximum, and these contact distances cluster around distances associated with energy minima. What it conveys is that the molecule tries to pick up a packing wherein there is a closest possible proximity between the neighboring molecules. By by achieving this, a maximum density or maximum true density of the material can be achieved. The next concept in crystal engineering is about the anisotropic interactions. When heteroatoms, which means different types of atoms, are present in the molecule, there is a possibility of formation of anisotropic interactions, and deviations can occur from pure close packing. The most important anisotropic interaction in organic crystal is hydrogen bonding, and it is also responsible for deviation from the rule of true density, from the achieving the true density. We will now move over to the technique of X-ray diffraction. More specifically, we will be talking about the powder X-ray diffraction, which is the most important technique for the characterization of the pharmaceutical powder samples from the angle of crystallography. Why are X-rays used in crystallography? X-rays are used to produce a diffraction pattern because their wavelength lambda is in the order of or smaller than the spacing d that exists between planes in a crystal. In principle, any wave impinging on a regular array of scatterers like the crystal lattice arrangement produces diffraction. To produce significant diffraction, the spacing between the scatterers, here scatterers are atomic planes in the crystal, and the wavelength of the impinging wave should be similar in size. However, visible light has too long a wavelength, typically 5,500 angstroms, to have to observe diffraction from the crystals, while the wavelengths of the X-rays are in the order of 0.722 angstrom, and it is on the order of atomic spacing. That is why we obtain diffraction using the X-rays when the crystals are studied using powder X-ray diffraction equipment. X-rays with high photon energies, that is above 5 to 10 keV and below the wavelength of 2 angstrom to 1 angstrom wavelength, are called as hard X-rays, while those with lower energies are called as soft X-rays. Due to their penetration ability, hard X-rays are widely used to image the inside of the objects, for example, in medical radiography or at airport security. Hard X-rays are also used in X-ray crystallography due to their reasonable penetration ability. For pharmaceutical solids, effective penetration depth into bulk surfaces about 150 to 400 micrometers, and their wavelength is similar to the size of the interatomic spaces. Because of these properties, hard X-rays are used for the purpose of PXRD. This picture shows that in water, the X-rays are able to penetrate 5 millimeter in depth. This diagram shows the energy of the X-rays and the purpose for which they are used. So the energy of 10 keV is used for X-ray crystallography, while higher energies are used for medical applications, while a still higher X-ray energy of more than 100 keV is used for airport security, that is baggage checking during the inside of the airports. The principle of the X-ray diffraction is shown in this picture. There is a phenomena of interference, and the interference could either be constructive interference or it could be destructive interference. Constructive interference means when the two waves are aligned to each other, then there is obtainment of a higher signal as the output. If they are opposite to each other, then the signal gets decreased or completely vanishes. You can see as soon as the rays become aligned to one another, the signal will become amplified here. And as soon as you have a reverse type of arrangement, the signal disappears. So this is the phenomena of interference. It could either be constructive interference and it could be destructive interference. In the constructive interference, we get a amplified signal at the end, which can be detected using a suitable detector. While in the case of destructive interference, the signal disappears because the rays have interacted in the opposite direction. There are certain conditions in the crystallography that need to be met to obtain constructive interference, and those are given by the Bragg's law. So Bragg's law provides a simplistic model to understand what conditions are required for diffraction. Bragg's law is n lambda is equal to 2d sine theta. Division of the Bragg's law, only constructive interference produces diffraction pattern. However, constructive interference occurs only when n lambda is equal to AB plus BC, or in other terms, n lambda is equal to 2B, since AB is equal to BC. So this is AB and this is BC. Sine theta is equal to AB by D. So in this triangle, sine theta will be equal to AB by D, which means AB is equal to D sine theta. And from here, it can be seen n lambda will be equal to 2D sine theta. So this is the interpretation of the Bragg's law. And this is the triangle which we were referring to for calculating or for replacing it with the sine theta. Two beams with identical wavelength and phase approach a crystalline solid and are scattered off two different atoms within it. The lower beam traverses an extra length of 2d sine theta. So this wave is going to traverse a distance which is 2d sine theta, because this one and this one. Constructive interference occurs when this length, that is 2d sine theta, is equal to an integer multiple of the wavelength of the radiation, which is nothing but the Bragg's law. That is why it is said 2 n lambda is equal to 2d sine theta. A diffractometer, the mechanical assembly that makes up the machine, consists of a sample holder, a detector arm, and a associated gearing, which is referred to as the goniometer. Most powder diffractometers typically have a arrangement which is called as Bragg-Brentano geometry, and this is the diagram of this Bragg-Brentano geometry of the powder X-ray diffraction machine. This is the sample. This red colored is the sample, and this black colored is the sample holder. This is the X-ray source, and passing through the divergence slit, the X-rays fall onto the sample. They are diffracted. There is an anti-scatter slit, and then it goes to a detector slit, and then to a monochromator, and then to a detector. This can move, and this detector can also move. So normally the angle that is traversed for the analysis of the samples of pharmaceuticals is 4 degrees to 40 degrees of 2 theta. So this is a goniometer. This is the X-ray tube. It can move. Then the detector can also move. This is the sample holder. The distance from X-ray focal spot to the sample is the same as from the sample to the detector, which means this distance and this distance are equal. The incident angle is always 1/2 of the detector angle, that is 2 theta. So this is the detector angle 2 theta, and this will always be half of this value. There are two configurations, theta to theta goniometer. Here the X-ray tube is stationary and the sample moves by the angle of theta, and the detector simultaneously moves by an angle to theta. An example of this equipment is Rigaku H3R. Rigaku is the name of the company who manufactures the PXRD machine. Theta theta goniometer. Here the sample is stationary in the horizontal position. The X-ray tube and the detector both move simultaneously over the angular range theta, and this arrangement exists in the equipment which is manufactured by Bruker T8 Advanced. This was present in our CIL till some time earlier. So this is the end of the presentation related to the crystalline state and powder X-ray diffraction. If you have any question, you can post them in the group made for the purpose of solid state pharmaceutics.